Okay, yeah, thank you very much. My name is Ed. The title of my talk is Deep Learning for Robotic Grasping. I work in a lab which is called the Dyson Robotics Lab. So Dyson have just recently started taking robotics quite seriously, as have a lot of other companies. And they've invested in our lab to try and get robots to kind of clear the house and do domestic chores. So one of the products that they've just started to sell in Japan and will be on sale this summer in the UK is a robotic vacuum cleaner. So this vacuum cleaner has a kind of a base station here where it charges itself, and it has a camera on top of the vacuum cleaner. So it goes around the house and it maps out the house itself, navigates autonomously around, and then it can find its way back to the power station once it's run out of battery. So this means you can just kind of set it off running all day and come back and the house will be nice and clean. So it uses computer vision, which is how robots use cameras to understand the world using images. And it uses computer vision to actually navigate and create a map of the world, such that it knows where it is at any one point in time. So that's the kind of current situation. But imagine in the future, instead of robots just going around on the floor and picking up dust, you want them to actually pick up objects and manipulate the room around you. So you've got a really messy room here. If you were to put that Dyson robot in this room, it would be able to navigate around these things, but it wouldn't really do the task that when you immediately look at this, you want it to do, which is tidy things away. So pick up these objects and put them away, maybe make the bed. There's all sorts of things that robot couldn't do. So my job in the lab is to try and make robots that can pick up objects and clear away these objects and stack shelves and do things like that. And manipulation is the key to this. So how can you get robots to pick up objects? So there's two aspects of my work. One is computer vision and one is robotics. Computer vision is how robots see things, well, how computers see things. And it's very, very sophisticated these days. It's almost the level of human capacity. And in fact, Patrick later on will show things that actually think computers can do that robots can't do. For example, building up really amazing reconstructions of the world. Robotics, on the other hand, and I define robotics as something which has a kind of a physical interpretation. So robots actually moving around in the world, interacting with the world, moving things around, doing the sort of tasks that you imagine robots actually doing, because just understanding the world is nothing unless the robot can actually do something in that world. And this is very, very difficult. So one of the things that computers can do very well these days is actually image recognition. So here you've got some examples of images that are thrown through this system that Google developed, and the computer is able to label them amazingly accurately. So you've got things like a person riding a motorcycle on a dirt road. This is something which 5 years ago we were nowhere near, but over the last few years we've really developed systems to achieve this. And it's all based on something called deep learning. So I'm wondering if many of you have heard what deep learning is, or maybe vaguely or not at all, maybe. Have you heard of the recent challenge where DeepMind beat the world champion at Go? This is a bit more popular. So deep learning is the technique that they actually use to get this computer to beat the world champion. So this is what my research is on. It's all about trying to get deep learning to work in the real world, physical world. But it's very, very difficult. Physical robots just tend to fall over a lot. So here's an example of a challenge in America. This is a thing that happens every year called the DARPA challenge. And this is an example of the sorts of failures that robots can exhibit. And typically, they're just not very good at things. They're very difficult to control once you've got some physical entity which is sensing the world and then responding to that world. It makes you realize how amazing the human body is, because we can somehow stand up, and we don't really know how we do it. It's very difficult. So there he's trying to turn the thing. He doesn't know he hasn't got it. Sorry? Oh, okay, sure, yeah. Hello. thing. Hello? Can you hear me? Yeah? Okay. So I'm going to talk about the challenge now and try to define this thing for you guys in terms of what I've been trying to do, and I'll guide you through the solution that I worked on and show you some of the results. So what I've got, this is the experimental setup. I have this literally next to me at my desk at work. So I have a robot arm and it has a camera on it. I'll tell you about that camera a bit more in a minute. And the idea is that it's got to go and pick up some object. Here I've got some stupid gun that we just had lying around in the office. But you know, the idea is it can pick up any object you throw in front of it. So this is the solution that I've got it to achieve. And it seems, I know it seems really simple, because when I first started doing manipulation, I thought, well, this is really simple stuff everyone's working on. It must be easy. But it is really difficult to actually to make progress. So it seems very simple, but when you think about picking up objects like, over the course of this talk, think about when you're grasping a glass, the things that you're actually processing. You have to first of all realize that this is the glass in front of you, and glasses are very difficult because you actually see right through them. So a robot will probably not even see the glass. It just sees some liquid in the middle and go, oh my God, what's going on? So you have to figure out the glass, you have to figure out where it is. And then humans also use a lot of tactile sensing. So we have very, very, very good skin, and we can really feel our way around objects. Like pretty much when we grasp objects, we sort of have a look down there. We use our vision to get our hand nearly there, and then we just go in and do the rest just with our fingers. But there's no such thing as robotic skin, and tactile sensing isn't something that has really been successful with robots. So we've really got to do this just with vision alone. Okay, so I'm going to define the task, the challenge. How can a robot pick up an object which it has never seen before? So you want it to be able to do things with unconstrained environments where it has never been there before, it's never seen these objects before. So this camera that I have on the robot is what is called a depth camera. So as well as a color image, it has a depth image. So this was originally invented for the Xbox. So the Microsoft Kinect is an example of a depth camera. So if you're playing games, you're kind of moving in front of the depth camera and it's tracking your body. This is exactly that kind of camera. So in a color image, for every pixel, you have a red and a green and a blue component. In the depth image, for each pixel, you have a distance. So it knows how far away the object is for every pixel. And these are what the two images look like from the previous setup that I just showed you. And my work is using the depth image, and I'll explain a little bit later on why I'm using depth images rather than color images. Basically just makes it a lot easier for me to do some of the interesting things that I'm doing. So this is the image that I have to deal with, and I want to basically figure out how to pick this up. Okay, so here's kind of the second challenge we have, or more of a refined question. Given a depth image of the object, what position should the gripper be sent to? So you've got this image. It's quite easy for us to say, well, maybe go kind of along the handle, but robots don't know it's a gun. They just see some kind of image, some pixels. They don't have this high-level intuition as to what this image actually means to them. So if we were to try to think about, we've got the gripper itself has two fingers. Okay, so we need to position that gripper somewhere in this image. So there are some very obvious positions on the handle here, as I just told you. Along the barrel there is another good one. Some of these might be okay, they might work, but it's not somewhere that you would naturally pick it up as a human. Again, this one kind of looks okay, might work, might not. And then you have some which definitely won't work. Okay. So what we want to do, given this image, we want to output a position of the gripper. So in the image, we want to have an X value, a Y value, and a theta defining the position of this gripper in the image. So computer vision historically was done by manually creating what we call features. So we'd say, for example, if we were describing this object, we'd say, okay, there's a kind of, there's a line slightly at a diagonal on the right-hand side, and then there's a sort of a rectangular white thing with another rectangular white thing. And we essentially build up a representation of images based on these handcrafted features. The problem with this is robots aren't the same as humans, so the way that we see things is not the way that robots see things. So the best way to get robots to actually understand images is to let them learn these things on their own. Rather than us telling them what they should be looking for the images, we try and get the robots to figure out on their own exactly what things in these images they should be looking out for. And this is kind of the core concept of deep learning, which is based on neural networks, and neural networks are modeled on the brain. So that the origins of neural networks is actually sort of bio-inspired neuroscience. And then from then we thought, okay, maybe this will be good for robotics. And for decades it didn't really work very well. But then very, very recently we've got sufficient computing power that we can actually have enough processing going on that we can do these complicated learning, which historically wasn't possible. Okay, so the third challenge. How can the robot learn this? By inspecting examples of successful grasp positions. So you want to show it lots of successful grasp positions and then get the robot to somehow learn from these where a good grasp position would be in a new image that it sees that it hasn't seen before. Okay, so I'm going to tell you a little bit about how deep learning works. So on the left-hand side we have our input. So those red dots represent the actual pixels. Each of those has a value. In this case, it's the depth value. So they have numbers associated with the pixels telling you how far away that pixel is from the camera. On the right-hand side, we have the output. So this is the grasp pose. And each of these represents a discrete or individual grasp pose. Okay. And these hidden layers in the middle, they're called hidden because we don't observe them. So we know what the output is, or we know what it should be. We know what the input is, but these hidden layers are the things that we're learning. This is kind of the bulk of the learning. We need to learn a function from the left to the right, and we need to do this by manipulating these middle layers. Okay, so what actually happens, you take these input pixels, and each of these input pixels on the left contributes towards this node in this first layer in the middle. I was told not to have any equations, but this is pretty much my only equation, but I do have another one later on, but it has colours in it, so I thought I'd make it a bit more, friendly. This is just white, so I hope it's not too boring. So basically, x is the value of this blue node, and it's just summing up all of these inputs. So the idea of neural networks is it's lots and lots of very, very simple sums, all contributing to something very, very complex. But each individual sum individual calculation is very, very simple. Okay, so these on the left contribute to the node there, and so on, and they also contribute to this one there, they also contribute to that one. And then all of the ones in this first layer contribute to the second layer. All of the ones in the second layer contribute to the third layer. All the ones in the third layer contribute to this final layer. And then you get an output. So you're having this kind of feed-forward nature whereby the input is making its way towards the output based on these sums. And this is what neural networks is. Okay, so in order to turn this into a thing where I can get the robot to pick up an object based on this, what happens is each of these output nodes has a value after sending all this data through. And what I do is I take the node which has the highest value and say, right, I'm going to move my arm to that particular node. And here's my second equation. So I actually lied before. You don't just add up the previous nodes. You actually add a weight to each one. So it's now big A times small a plus big B times small b. So each of these nodes on the left is associated with another weight. Okay. And what the idea of deep learning is to find out which weights make the best network, which weights map your input image to your output pose the best way. So if you were to randomly associate these weights, give these weights a random number, your input would just give some random output. What you want to do is to force inputs to give certain outputs and then manipulate the weights in order that these inputs do give those outputs. So you have all these kind of random weights in the middle, and you can see that they're just sort of giving different output poses. But what I want to do is say, right, I know, for example here, the grass should be kind of in the middle and a bit, going across the handle there, and I'm going to say, right, given this particular input image, I want it to learn this output pose. Okay, so I want there to be a high number on this green node which is associated with that output pose. Which weights, given this input, will give this output. Okay, so I could start off with randomizing these weights, and it will give me this situation here. This is bad because I actually want that node, the green node associated with the white line, to be very high. What I do is I change these weights over and over and over again until they become, until they give me what I want. And then I train this on loads and loads and loads and loads and loads of different objects, thousands, sometimes millions, until you get a system where you're taking the same inputs that you showed it and it's giving the correct outputs that you want. And then the idea is when you show it a new image, it will figure out, it's learned some function which will give it the appropriate outputs corresponding to this new input. And this is what deep learning is. I'm just going to talk a little bit about how deep learning is slightly different with images. So with images, for each of these blue layers, you actually have a set of what we call feature maps. And each of these feature maps is essentially like a filter, and it's looking for certain things in the image. Okay. This first layer looks for very, very simple, primitive shapes like edges and lines. So if I were to train this on color images, it would give me these kind of filters for the first layer. So you've got some edges, you've got lines, you've got some sort of blocky type things. But they're all very, very, very simple things, but it's learned this automatically. In the middle layer, then each of these is a function of the first layers. So this is what the second layer looks like. Slightly more complex, more abstracted images. You've got things like multiple lines, you've got some textures, you've got circles, but each of these is a function of the ones in the first layer. So for example, a circle might be a line going across, then a line going down, then a line going across below that, and a line going up, and maybe some on the corners as well. So you get these sort of, this hierarchical nature where these ones built up on ones in the first layer. And then when you get to the third layer, they're even more abstract. And in fact, when you get to these high levels, you start to see interesting things. You might recognize some of these. I think that's like a duck or something, a balloon, whatever they are. They're kind of, I'm familiar with these kind of images. And it's amazing because there's a lot of neuroscience research which shows that this is how humans process images. So we have this hierarchical nature where we have a first level which is looking for very primitive shapes like edges and lines and circles. Then we build this up, and by the top layer we're then seeing faces and whatever things that we have intuitive understanding of. So it's amazing that we've taught these robots to do things automatically, and it turns out that it does things in the same way that humans do things. So this is really good evidence that the way that we're training robots is the correct way to do it. So what I'm doing is I'm passing this image through this network, through this hierarchy, and giving some output pose position of the grasp, of the gripper. And that's called convolutional neural networks. Okay, so the final question that I want to address is how can we generate training data of sufficient scale? So one of the reasons why deep learning has only recently been successful is that it requires loads and loads of training data. So if you were to use the kind of handcrafted features that I talked about, where you kind of say, you say, is there like a rectangle or a square or a circle in the image? These things don't need so much training data because we're already injecting a lot of human knowledge into the system. When we're getting robots to learn on their own, just by providing inputs and outputs, there is the potential for it to learn the wrong things unless we provide it with enough training data. So imagine we only showed it 4 examples of pixels on the x-axis and grasp position on the y-axis. What we want it to learn, possibly, is this function here. But because a neural network has the capacity to learn so many complicated functions, it's so rich in its ability to learn inputs or outputs in a very, very complex manner, that it might learn something like this, and it probably would do. Okay. So this is a good thing about neural networks. They can learn very, very complex functions, but a bad thing because if you don't give it enough data, it will learn the wrong complex function. So what we need to do is give it loads and loads and loads of data, and then it will still learn a complex function, but that complex function will be the right one instead of the wrong one. So what I want to do is gather loads and loads of images with correct grasps and also ones with incorrect grasps. There's a few ways to do this. One way is the way that Google do it. They recently released some work where they have a warehouse with 40 robots grasping objects day in, day out for 3 or 4 months. And that's their solution to getting this training data. The robots go in, try to pick up objects, and then they see if they're successful or not. This is fine if you're Google and you've got money to spend on 40 robots that can run for 4 months. But it's not really scalable, because if you were to want to train it on another object, then it would have to train for another 4 months. And also, if you don't have Google's budget, then you're never going to be able to compete with them. So that's not going to work. Another solution is to get humans to label things. So we could imagine we show humans lots of objects and say, right, can you put on a little mark on this object as to where the object should be grasped? You can imagine doing that as well, but again, it's not very scalable, because you have to get people to do it. You have to pay them or bully them into doing it. And again, you don't really want to have humans involved in this. We can be doing better things with our time. So this isn't really a viable solution. The solution that I do actually work on is using simulation. So I want to simulate the grasping, and so I can do everything on a computer. I don't have to do it in the real world. And from this simulation, I can get some results which I can use then use to train the robot. So I have a physics simulator here on the left, and I take an image of the object that I'm simulating picking up, and I simulate that depth image, and then it outputs some scores for every different position that the grip is going to. And this is the reason why I'm using depth images instead of color images. There's 2 reasons. One is that I can train with lots of CAD models. So I can throw lots of CAD models, sort of 3D meshes into the simulator, and because of the 3D nature of them, the robot can pick these up. And from a 3D object, I can generate a synthetic depth image, because a depth image, all it needs is shape. It doesn't care about the color of the objects. If I wanted to train with color images, I would have to have a massive database of colored 3D objects, and that just doesn't exist. There are lots of databases with CAD models where you've just got the shape, but to get a color for that object, it doesn't really exist at the moment. So this is something we can't really work on. So this is a video now of what my simulator actually looks like. So in this example, I'm using a kind of toy aeroplane. The idea is not to learn how to pick up aeroplanes, but what I do is I show it loads and loads, I show it thousands and thousands of objects, and it tries these kind of graphs on these objects. And I show it an airplane, but then I show it a little, a cube, and then I show it a pint glass. And then I show it one of these, and I show it loads and loads of objects. And the idea is that it's learning a generic understanding of how to go in and grasp a shape. It doesn't care about the identity of that object. It doesn't know about the identity of it. That's not what it's learning. Remember, I'm telling it from the input image, where should the gripper go to? It's not learning what the object is. All it cares about is transferring this data through the neural network from the image space to the space where it should be grasping the object. And I generate this data just by simulating these grasps. So the important thing to remember when I show the results in a minute is that it's been trained on completely separate objects that it is being tested on. So the objects that it's been testing on, it's never seen before. It's only been trained on these kind of objects. And these are some examples of the kind of objects in the databases that I've been using that you might train it on. So all sorts of range of different objects with different kind of shapes, different scales. So that aeroplane there, doesn't matter what scale it is. It's the idea of having some kind of interesting shape and figuring out where to actually pick up that object. That's the important thing. And now I'm going to show you some of the results of my work. So what happens, the robot starts off over on the right. It takes an image of the cube, moves over to the top of it, rotates, goes down, and picks up that object. So you can see I've got rubber bands on the gripper, which is just proof of how bad robots are, that even very expensive robots still have to do tweaky things like put rubber bands So I'm going to start with, here are some kind of quite simple objects, sort of blocky shapes. Then I've got some more real objects that are kind of block-like in nature, but you know, they're not actual blocks. It's actually a cylinder, but it still kind of knows where to go and grasp it. Of course, the image of this Pritt stick thing is the same as a cube when you look at it from the top. Here we've got a stapler. Essentially what it's doing is looking for kind of parallel edges in the object to pick up. So when you pick up something, you want to find two edges, and if they're parallel to each other, that means you can go in and grasp that object. Here we've got a remote controller. This is actually the remote that is used to control the robot. So I'm sometimes worried that it's going to start controlling itself and take over the world or something like that. But it hasn't done that yet. Here we've got some pliers. This one I had to do a few times to get a good video because it's very difficult to get a good grasp and it almost falls off. You can just about see. Oh. And this one's interesting because there were no objects of this nature in my training data set actually. There's nothing with this kind of cylindrical nature I looked. But it's still finding these kind of edges to go in and grasp. And here we've got the gun, which I showed you at the beginning. And this is an example of one of the graphs that it achieves. Okay, so this is pretty much the end of my talk. To conclude, my idea is to try and simulate everything, do lots and lots of simulations, and then use deep learning from this data that you've got from the simulation to train a robot to pick things up. And given a bit of time, we might then be able to get robots to clean rooms and turn them into something like this. Thank you very much for listening.